Hi there, this is Professor Shannon Gracie. We're working out of the Precalculus Enhanced with Graphing Utilities text by Sullivan and Sullivan. And we will be covering mathematical models today, building functions. This is a really important skill to have for calculus. When you get into calculus, you'll be optimizing functions and so that if you know how to write a function in terms of a single variable given secondary information, that's going to be really helpful for you. So here we go. Let's warm up by just remembering some of these basic formulas. So the sum of angles in a triangle is good, 180 degrees. The distance between the ordered pairs x1, y1, and x2, y2 is d equals the square root of x2 minus x1 quantity squared plus y2 minus y1 the quantity squared. And then in general, we can answer the next one as this distance is equal to the change in x squared plus the change in y squared. The area of a rectangle, good. The area equals length times width, or base times height if you prefer. Perimeter is the sum of the lengths of the sides of a polygon. And the area of a circle is area equals pi r squared. Pythagorean theorem states that the sum of the squares of the sides equals the square of the hypotenuse. So in this model, we'd have a squared plus b squared equals c squared. The volume of a right circular cylinder, like a Coke can, is volume equals, so its base is a circle, so pi r squared, and then times the height gives you the volume. Right circular cone is a third of that, so you'd have 1/3 pi r squared times h. The volume of a sphere is 4/3 pi r cubed. The volume of a right rectangular prism is length times width times height, and the volume of a right rectangular pyramid is 1/3 of that. All right. Okay, so now that we've reviewed some of the basic formulas, let's take a look at these problems here. So we have this point x and y as a point on the graph of y equals 1 over x. So they want us to express the distance d from the point to the origin as a function of x. So let's think about what we have here. The origin is the ordered pair 0, 0, good. And then the point on the graph, point P is equal to x comma y, but what is y? Good, y is 1 over x, so we'd have x comma 1 over x. So now we're working with the distance formula. So the distance will be the square root of x minus 0 squared plus y, which was 1 over x, minus 0 squared. So we'll get the distance is the square root of x squared plus 1 over x squared. So now we've written this as a function of the distance. And actually, you know what? Let's do this. Let's say distance as a function of x. Distance as a function of x. All right, so now we are using a graphing utility to graph this function that we found. Okay, so let's see what we have going on. So it was the square root of x squared plus quantity 1 divided by x squared, and then I'll end the, whoops, I'll end it with a parenthesis. And I didn't do squared, did I? So we got to go second, insert. There we go. I think we've got it now. Oops, I must have missed something. Let's see what we have. Oh, okay. I need to add in another parenthesis here. Okay, so if we graph this, this is what it looks like. Alrighty, and then our next job is for what value or values of x is the distance smallest? So we can go to a command here. If we go to second, calculate minimum, and this is symmetric. So let me get to this side. Do left bound here, right bound here. So it looks like we've got a minimum distance of 1.4. Now let's make sure we're answering the question here, because yeah, sorry, I saw that here. For what values of x is d the smallest? So d is the smallest at approximately plus or minus 1.41. And that occurs when x is plus or minus 1. You can see from the symmetry of the graph. So I'm going to go ahead and copy this so you can see the command that I used. Okay. And we'll answer the questions when x is plus or minus 1. Okay so far? Good. All right, so the next problem here, a right triangle has one vertex on the graph of y equals 9 minus x squared, where x is greater than 0, at xy, another at the origin, and the third on the positive x-axis at x0, so somewhere x0. So let's take a look at the picture of this. So the graph was y is 9 minus x squared. So we have x and y. Just do the regular scale. So 9 minus x squared. So if x is 0, y is 9. So I'm going to put an open circle because it said that x was greater than 0. And then if x is 1, I think we'll have an ordered pair at 8. I'm working with 9 minus y is 9 minus x squared. And then if x is 2, we'll have an ordered pair at 5, or a y value of 5. If x is 3, we'll be down at 0. If x is 4, we'd be at negative 7. And then we'll keep going from there. So that's our graph of y. Now, at some point here, we don't know where exactly, but at some point here at x comma 0, so it could be anywhere along this axis here, the positive axis, I'm just going to write it in right here and call this x comma 0. And then we're going to have a point somewhere. It said that we also had a point at the origin, right? So that's at 0, 0, and somewhere on the graph. So we'll just say right here, we don't know exactly what that ordered pair is. So we'll just call it xy. So here's the picture of our right triangle here. Let me highlight that in red. It's not showing up very well in the green. Okay, so now let's take a look at what we have going on. So when we take a look at this one, we're going to have, they're asking us to find the area as a function of x. So let's just take a look. We know that area of a triangle is half times base times height. Well, the base is just x, and the height is equal to y, which means the height is equal to 9 minus x squared. So plugging that in, we'll have area is 1/2 times x times 9 minus x squared. And if you multiply, we'll be doing area in terms of x. So area in terms of x will give us, let's see, 9x over 2 minus x cubed over 2. And we're done. I think that's all we were asked to do in this problem. Okay. Next up, a rectangle is inscribed in a semicircle of radius 2. So let the point xy be the point in quadrant 1 that is a vertex of the rectangle and is on the circle. So here we go. So a semicircle of radius 2 means we'll have an ordered pair at 2, 0, at 0, 2, and at negative 2, 0. So we've got this semicircle here. Okay, so here's our semicircle. And then what we're doing is we're inscribing some sort of rectangle here. Oh, that's not a very good one. Some sort of rectangle inside the semicircle. So, and then we're going to use this ordered pair, x comma y. So that gives us this value here. This length here is just going to be good, x. And then this length here is going to be y. So let's see. We've got our visual going on. So again, we have the base of the rectangle is going to be good 2 x's, right? So you've got symmetry going on there. The height of the rectangle is y. So the height of the rectangle is going to be equal to So let's do a little bit of work here. So recall that x squared plus y squared equal to 2 squared is a circle with radius 2. If you isolate y squared, you'd have 4 minus x squared. And then if you square root both sides, we're using the positive side of the result, but you would get y is equal to plus or minus root 4 minus x squared. And so the top half of the semicircle is the positive root. So the height will be root 4 minus x squared. Okay, so express the area of the rectangle as a function of x. So area in general is length times width. Actually, on this one, I guess I'll do base times height since that's the wording we used. So area in terms of x is going to be 2x is the base, and the square root of 4 minus x squared is the height. And we're done with that part of it. Okay, now let's express the perimeter of the rectangle as a function of x. So you'd be doubling the base and doubling the height for perimeter in terms of x. So we would have 2 times 2x plus 2 times root 4 minus x squared. So perimeter in terms of x will be 4x plus 2 root 4 minus x squared. So on these, I think it would be good to do the graph using our graphing calculator instead of by hand. So let's take a look at what we have going on here. So let's go to our y equals. Clear. So we'll do our area graph first. So it'll be 2 times x times the square root of 4 minus x squared and let's see. We'll go ahead and let's go ahead and we'll just graph it. Interesting graph there. Okay, so let's zoom in on this so we can get a better idea. It looks like. So I'm not sure why it doesn't go all the way down to 0. Let's play around with the window. It might be something to do with the resolution. So we want x to go to 3. So I'm going to call it 3.1. And we don't need to consider the negative for x. So let's call this negative 0.1 to start. And then the y minimum we can do again a negative 0.1. And then the y maximum, let's just say 5. So let's graph that and see if it does anything better for us. Still strange, because if you plug in 2, you would get 0. So we need to work with the resolution. It's looking a little better, but we're not quite there yet. So let's do the resolution. I don't know. We'll try this at 2. Does that do anything? No. Alrighty. If not, we'll just finish the graph ourselves. How about y x resolution, y max, y min, x scale? I don't know. We could try 10 for resolution. It's not doing anything else. I'll have to get back to you guys on that one. We'll go ahead, we'll copy this, and then we'll fill in the rest of the ordered pairs. Okay, so this should end up going down. We know for sure there's going to be an ordered pair. If you plug in to the original, it'd be at 0. So I'm thinking it's going to go something like that. All right, so for what value of x is the area largest? Well, again, we'll do our maximum feature. So if we go to second, calculate maximum. So we go to the left of the maximum, hit enter. And then the right of the maximum, hit enter again. And then we get our maximum is at approximately x is 1.41. And it's a maximum of y equal to 4. So when x, the max occurs, and x is approximately 1.41, a of x is the largest. Okay, so we do the same thing with the perimeter function. So the perimeter function, we have we'll go to our y equals. So now we'll have 4 times x, and instead of being multiplying, we're adding. And then if we insert 2 times that radical, I think we'll be good. So let's graph this guy. So this one, we're not getting a good view of our graph here. So let's go to, we'll try zoom fit, see if it works. Okay, that's better. Again, I want to make sure our graph is going okay, because when x is 2, the second part will zero out and we'll be up at 8. So this one actually looks like it's doing better. So let's take our screenshot here. Okay, we'll paste it over here. And then let's see for what value of x the perimeter is largest. Going back to our calculator, if we go to second, calculate maximum again. Left bound here. Let's make sure you're to the right of that maximum. I think we're good here. So when x is approximately 1.79, we get a maximum of 8.94. So 1.79. 1.79. P of x is the largest. Okay, so moving right along. Two cars leave an intersection at the same time. One is headed south at a constant speed of 30 miles per hour, and the other is headed west at a constant speed of 40 miles per hour. Build a model that expresses the distance d between the cars as a function of time. So let's just take a look. So we've got our little intersection going on, and then that first car is heading west at a rate of 30 miles per hour. So remember that distance equals rate times time. So they're traveling the same amount of time. So distance 1 would be rate 1 times time 1. So distance 1 would be, our first rate is 30 miles per hour times time 1. Distance 2, they'll be getting a little farther because they're going faster. So distance 2 is equal to rate 2 times time 2. So distance 2 is 40 times time 2. But they're going the same amount of time. So time 1 equals time 2. So distance 1 is going to be 30t, and distance 2 is going to be 40 times t. So what we need to find out, an expression for this distance here. So for that distance, we'll use the distance formula. So our distance here is going to be the first distance squared plus that second distance squared. So actually, I guess you could sort of, because this makes a right, angle there. So I suppose you could just say that you're using the Pythagorean theorem. It's all kind of similar. But you could call this point here, if you think about where they're leaving from, you could call this here, say, an origin. So distance d in the red would be root 30t minus 0 squared plus 40t minus 0, the quantity squared. So distance would be root 30t, or not 30, my bad. 30 times 30, I'll write an extra step. 30t the quantity squared plus 40t the quantity squared. So the distance will be the square root of 900t squared plus 1600t squared. So that would give us 2500 t squared. So we would get the distance is 50t. We don't need to worry about the plus or minus because time is positive. So this actually, and you know what I should have done, is I should have done distance in terms of time. So distance in terms of time is and you're done. Okay. So one more problem and then we'll be done with chapter 2. So you guys are making great progress. Okay. An open box with a square base is required to have a volume of 10 cubic feet. So we need to express the amount A of material used to make such a box as a function of the length x of a side of the square base. So with something like this, it's good to make a picture. So you've got, this box as a square base. So here, these are both x. And then you've got this height of the box going up. So you end up with sort of a surface area problem. So you have, you know, this this region here of the box, this bottom part, the area for this part of the box is going to be what? So area of the base of the box is going to be x times x, which is x squared. Good so far? And now if you look at this right here, we're going to have four measures that have the same area. So this area of the side is equal to x times h. Well, we've been given, so that's the yellow area. And so we've been also given information. We've been given information that the volume of the box is equal to 10. So you end up with 10 is equal to x squared times h. So if you isolate h, you get 10 over x squared is h. So let's put this together. Okay? So the amount of material in terms of x is going to be that area of the base of the box, which was x squared, plus 4 of those yellow areas. So that was x times, and what was h? Good, h was 10 over x squared. So in for h, we're plugging in 10 over x squared. So now area in terms of x alone is x squared plus 40. We can divide out one factor from the bottom and that x in the numerator, so we get 40 over x. And we're done with that part. Okay, so using this formula, how much material is required for a base 1 foot by 1 foot? So basically, x, this is telling us that x is 1. So using our formula, area in terms of x is x squared plus 40 over x. Area when x is 1 will be 1 squared plus 40 over 1. So area, or not area, amount of material when x is 1 is going to be 41. And that'll be feet squared. Okay, so how much material is required for a base 2 feet by 2 feet? Well, area when x, or not, I apologize, I keep saying area. Amount of material needed when x is 2 is 2 squared plus 40 divided by 2. So we'll get 4 plus 20, so 24 feet squared. And then let's use our graphing material, or our graphing utility. So our function that we had gotten was, we had x squared plus 40 divided by x. Let's see what we have. So this one we're going to have to change our zoom. So I'm going to go to zoom fit again. See what the window is. Okay, I guess that's fine. You know, let's try one more thing. Sometimes it looks odd when you do it at first, and let's go ahead and just zoom out a few times and see what we get. So we're not interested in negative values of x. So let's see what we have. So x minimum, we'll put 0. And let's see what our graph looks like. Oop. Well, again, not very illuminating. Let's do our window again. We don't need low values of y, or negative values for y. So let's see. Still not super happy with it. So for my x, the maximum that x can be, I believe, let's try this. Let's graph this and see what we get. That's a nicer picture. We'll copy this guy. All right, so for what value of x is the amount of material the smallest? So we're interested in that minimum right there, that local minimum. So let's go ahead and go here. Let's go to second, calculate. Now we're doing minimum. I can't see where my deal is. Oh, there it is. There we go. Now it started going up again. And then right bound. And we get when x is approximately 2.71. All right. Smallest when x is approximately 2.71 feet. And we're all set. So you guys have a great evening. I will be talking to you soon. Bye.